Let's solve another thermodynamic problem where we'll use entropy as a vital part of our solution. Water within a piston cylinder assembly, initially at 10 psi and 500 degrees Fahrenheit, undergoes an internally reversible process to 80 psi and 800 degrees Fahrenheit, during which the temperature varies linearly with specific entropy. For the water, determine the work and heat transfer, each in BTUs per pound mass. Neglect kinetic and potential energy effects. Let's lay out our storyboard. We have a piston cylinder assembly. The system is going to be the water molecules contained within the piston cylinder. And here's what we were given. We know that the initial state, the temperature is 500 degrees Fahrenheit, which is a temperature of 960 degrees Rankine. The pressure is 10 psi. Now, I haven't shown you the details, but if I look in the saturation table at 10 psi, I will find that the saturation temperature is below 500 degrees Fahrenheit. And that tells me that this is a superheated vapor state. And the same thing happens at state 2. Both of these states can easily be determined to be superheated vapor by just looking in the saturation table under these two pressures. How are we going to model this? Well, we know it's a closed system. We were told to ignore any changes in kinetic and potential energy. This is an internally reversible process. And we were told that the temperature varies linearly with the entropy. What does that mean? Well, before we look at the drawing, let's be very specific about what we want to find. We want to find the work per unit mass. In other words, we call that small w. And the heat transfer per unit mass, we'll call that small q. So let's look at a TS diagram. We've got our vapor dome. And we've got state 1. State 1 is at 500 degrees Fahrenheit, 10 psi, and it is a superheated vapor. State 2 is also a superheated vapor. It exists at 80 psi and 800 degrees Fahrenheit. And what we're told is that this is an internally reversible process, and the path is given. The path of the process from state 1 to state 2 is a temperature that varies linearly with entropy. So it's a straight line between state 1 and state 2. Now we know for an internally reversible process that the heat transfer is the area underneath the curve. So we could write an equation for this line and integrate it, but it's easier if we just recognize that if we exchange this triangular area for this triangular area, that we would have the same area, and that happens at the average temperature. So Q could be written as the average temperature times the change in entropy. So let's do everything with small letters. So Q is just the heat transfer per unit mass. And we know that the heat transfer for an internally reversible process is the integral from state 1 to state 2 of TdS. Now, since we're using the average temperature to calculate the area under the curve, we can say that that's just T times the change in specific entropy. Now, the average temperature is just T1 plus T2 over 2, and that's 960R plus 1260R over 2. So we end up with an average temperature of 1,110 degrees R. So let's go to the superheat tables. The first one would be at 10 psi and 500 degrees Fahrenheit. I'm going to get a value here for S1 and U1. And at 80 psi and 800 degrees Fahrenheit, I'll get a value for S2 and U2. Now I can solve for the heat transfer Q. Q is just the average temperature times the change in specific entropy. We calculated the average temperature to be 1,110 degrees Rankine, and S2 was 1.8700, subtract S1, 1.9690, having units of BTUs per pound mass R. We calculate that the heat transfer that takes place during this process is minus 109.9 BTUs per pound mass of water within the system. And the negative sign, of course, indicates that heat transfers energy from the system to the surroundings. Now, we can solve for the work term using an energy balance. For a closed system where we're ignoring changes in kinetic and potential energy, our energy balance is just delta U is Q minus W. That's in terms of energy. We can divide the entire equation by the mass, and then we get delta U is Q minus W, all small letters. All of these are energy per unit mass. So I'm going to rearrange and solve for work, which is what I want to find. And I end up with W is Q minus the change in internal energy. Well, Q, we just solved for Q. It's minus 109.9 BTUs per pound mass. I'm going to subtract from that the quantity U2 minus U1, where I've inserted their respective values here. And I get that the work term is minus 220.1 BTUs per pound mass. And again, the negative sign indicates that work has to be done on the system in order for this process to take place.